All right, guys, welcome back. In this video, we're going to look at definite integrals with u-substitution. Okay, so we've done a little bit with definite integrals before, right? The fundamental theorem of calculus. But now we're going to see like what happens when we need u-substitution to take the integral. Okay, so my first example, I want to go from -1 to 1 of x times x squared plus 1 cubed dx. Okay, so remember, you still have to know how to integrate it before you can plug in the bounds. So we look at that first and we ask ourselves, all right, well, we can't distribute the x in because of the power here, but we do have something that's a little more complicated raised to a power. So perhaps that's going to be our u. All right, so let's see if that works out for us. So we take the derivative of the dx to the right. And let's see, we've got an x times a dx, we just need a 2. And we know we can compensate for that. Okay, now when we go to rewrite it, don't write the bounds just yet. You have u cubed, right? Because the x squared plus 1 to the third is what you, so there's your u cubed, and then 2x dx is your du. The problem is you are integrating with u's, and these bounds go with x's. Okay, so when you use u-substitution, you need to change the bounds. Okay, so when you use u-substitution with definite integration, you need to change the bounds. Okay, so you're going to use your u equation, and you're going to find a u for the top, and you're going to find a u for the bottom, and these are bounds. Okay, so what are you going to do? Well, you're going to plug in the bounds that you're given. Those are x values. So you're literally going to plug those in as x values into the u equation. All right, and so like if I do 1 squared plus 1, I get 2. So my top bound is now 2. And for the bottom, I'm going to plug in a -1. Well, -1 squared plus 1 is also 2. All right, so I've changed my bounds. All right, and so now I'm ready to integrate. But this one's really good. This one's really nice because when you integrate and the bounds match, there's a property that says that's automatically 0, and you're done. Okay, and so again, that one's done. And the good thing about changing the bounds is that once you change the bounds, you'll see in a little bit that you actually never have to plug the x's back in. So once you change the bounds, you never have to plug the x's back in. All right, so let's get to some more examples so you can see that. All right, so number 2, let's look at the integral from 0 to pi over 2 of cosine of 2/3 x dx. Okay, so I've thrown a trig one back in there at you. All right, but I only have the one trig function. So probably, all right, what's inside parentheses is your u. Because if the trig function was a u, then I would need another trig function for du. All right, du is, let's see, 2/3 times dx. So I can compensate for that. I need a 2/3 in the integral and a reciprocal outside. All right, so the reciprocal comes down. That leaves me to integrate cosine of u du. All right, but because I'm using u-substitution, I need to change my bounds. All right, so for the top, I'm going to plug pi over 2 in for x. And I'm going to multiply that by 2/3, and I get pi over 3. So my top bound is pi over 3. All right, and then for the bottom, I'm going to plug in 0. Well, 2/3 times 0 is 0. Okay. All right, now I'm ready to integrate. The 3/2 will stay. I have to remember the integral of cosine of u is sine of u. All right. But because it's definite integration, I'm going to put, instead of putting plus c, I'm going to put my bounds. And because I changed my bounds to represent u's, I never have to plug 2/3 x back in, okay? I literally get to plug these numbers in place of u, all right? So I get 3/2 sine of pi over 3 minus 3/2 sine of 0. All right, well, hopefully remember sine of 0 is 0, but you are expected to know sine of pi over 3. All right, so we got to think about our 3 angles, all right, which one is pi over 3? Well, pi over 3 is bigger than pi over 6, so this one's the pi over 3, all right, and then when I do my hand trick, all right, my ordered pair is 1/2 and the square root of 3 over 2. And the sine value is the second one. So this becomes 3/2 times the square root of 3 over 2. All right, and just so I'm showing you the work, sine of 0 is 0. You should definitely know that. And when I simplify, that goes away. And I can simplify, I can squeeze this together just a little bit. All right, so I get 3 square root of 3 over 4. All right, so we're just going to keep on doing a couple more practice problems just to make sure that you've got the hang of it. All right, so I don't want to lose all this dead space here. So, all right, let's integrate from 0 to 4 of x over the square root 2x plus 1 dx. All right, so I see a radical on the bottom especially, right? And so what's under the radical? Let's see if that's going to be my u. All right, that would force du to be 2 dx. I can definitely compensate for the 2. I have the dx, but I also have extra. All right, so we just learned about what to do with extra. So if there's extra, right, you take your u equation and you solve for x. Right, so let's see, that's u plus 1 equals 2x. X equals, when I divide by 2, that's the same thing as multiplying by 1/2. Okay, so let's come back over here and put it all together. We've got a 1/2 in front. Do not fill in the bounds because we're going to change those. The square root on the bottom comes up as u to the negative 1/2. The x turns into 1/2 times u plus 1, and the 2 dx becomes my du. Okay? All right, and we need to get our bounds. So I need a top bound and a bottom bound. All right? And I get those by plugging in the x into the u equation. So 2 times 4 is 8, 8 minus 1 is 7, 2 times 0 is 0, minus 1 is negative 1. I did something wrong. Oh, I wrote this wrong. All right, 2 seconds. This is supposed to be 2x plus 1. So then this becomes u minus 1, and this becomes u minus 1. This becomes u minus 1. Sorry, guys. I knew that looked weird. All right, because I've done this problem before. All right, so then that definitely changes my bounds. All right, 2x plus 1 is 9, and then 1. All right, so my new bounds are 1 and 9. All right, now I need to do a little bit more simplifying before I can actually integrate. So I'm going to pull this 1/2 to the front, and that makes a 1/4. And I'm going to distribute my u to the negative 1/2 into my parentheses, since I don't have a product rule. All right, and that is a little bit easier to work with. Okay? All right, sorry, I didn't mean to roll up so fast. All right, so we're going to keep the 1/4. We're going to integrate by adding a power, dividing by the new power, adding a power, dividing by the new power. But again, instead of plus c, we're going to put our bounds. And because we changed our bounds to be values of u, We do not have to plug the 2x plus 1 back in. Okay, so that actually makes it really nice. All right, so I'm going to distribute my 1/4 and plug in my bounds at the same time. So I know that's a lot. All right, so 1/4 times 2/3 is, let's see, 1/6. And then I'm going to plug in 9. All right, but it's hard to raise something to a fractional power. So I'm going to remind myself that 3/2 is the same as the square root cubed. Okay, and then let's see, 1/4 times -2. And then that's the square root of 9. All right, so that's the first piece. And then I'm going to subtract. And I still have to distribute the 1/4. But now I'm going to plug in a 1. Okay, well, 1 raised to a power is 1. All right, so now I just need to get my calculator brain going. All right, so the square root of 9 is 3. 3 cubed is 27. 27 over 6 will reduce in a minute. Square root of 9 is 3. Distribute the negative. All right, well, actually, I can put my pieces that have a common denominator together already. And then I can put those pieces that have a common denominator already. 26 over 6 reduces to 13 over 3 minus 1, which is 3 over 3. So put it all together, I should get 10 thirds. Okay. All right, so it just takes a little bit of practice. All right, got just a couple more for us. Want to make sure you have plenty of examples. All right, so let's integrate from 1 to 2. X minus 1 times 2 minus x to the 1/2. Okay, dx. Well, because I have one binomial raised to a power, that particular binomial is probably my u. All right, so du, let's see, it would be -1 dx. And that's -1 times dx. That's not the same thing as x minus 1 times dx. So I can compensate for the -1. The reciprocal of -1 is still -1. But I have extra. I have a binomial that's extra. Okay? So what I need to figure out, all right, is come over here and solve for x. All right, the easiest way to do that, though, is to add the x to the left, subtract the u to the right, okay? And then when I bring that over here, x minus 1 becomes 2 minus u minus 1. All right, because I plugged in for x, which was 2 minus u, but I still have to subtract 1. So I put all that together and I get 1 minus u. The 2 minus x raised to the 1/2 is my original u to the 1/2. Still have the -1 in front. The dx times -1 is my du. And so the only thing I have left to do is change my bounds. Okay, so I need a top bound by plugging in 2 for x. And I need a bottom bound by plugging in 1 for x. Interesting. All right, now, what if I don't feel like working with a negative? Well, it kind of works out to my benefit here because remember there's a property that says if the bounds are in the wrong order, you can actually switch them if you prefer, and then it makes the whole integral negative, which in this case, 2 negatives would make a positive. So I can switch those and it gets rid of the negative here in front. So that actually works out pretty nice. And I need to distribute. Don't forget to add powers when you multiply like that. And now I'm ready to integrate. All right, so we're going to add a power, divide by the new power, add a power, divide by the new power, plug in my bounds. All right, well, 1 raised to a power is still 1. Both times I raise it. And then when I subtract and plug in 0, those give me zeros. So all I have to do is figure out what is 2/3 minus 2/5. 2/3 minus 2/5. So I'm going to get a common denominator of 15. This becomes 10. This becomes 6. And I get 4/15. All right. All right. The next two aren't going to take quite as long, and then we'll be done with this video. All right. So example number 5, let's throw some e's in there for our bounds. All right. dx over x natural log of x. Well, remember, we said we don't actually have an integral for ln of x, so that should be my u. Okay? Well, du is 1 over x dx, which is actually the same thing as dx over x. So I actually do have du. Where is u? It's on the bottom. Okay? So if I bring it up, it becomes u to the negative 1. And du is everything else, but I do need to change my bounds. All right, so for the top, ln of e squared is something you should be able to simplify. And on the bottom, ln of e is also something you should be able to simplify. All right, when I integrate u to the negative 1 du, I get natural log of the absolute value of u, and then I can plug in my bounds. So I'm going to plug in 2. The absolute value of 2 is still 2. And I'm going to plug in 1, so I can drop the absolute values. You are expected to know that ln of 1 is 0. And so when I put all that together, I just get ln of 2. All right, that one was nice and quick. And last one for this video, number 6. Let's look at the integral from 1 to 2 of e raised to the 1 minus x dx. All right, so remember, if you integrate something with an e, especially if there's only one e in the whole problem, what it is raised to is more than likely your u. Du then would be, let's see, negative 1 dx, which I can compensate for as long as I put the reciprocal in front. All right, and so what does that give me? That gives me negative 1 times the integral of e to the u du. But I want to change my bounds so that I never have to plug x's back in. All right, so for the top, 1 minus 2 is negative 1. For the bottom, 1 minus 1 is 0. All right, here's another one where you're welcome to flip it over, right, if you feel more comfortable doing that, right? But it does make your integral positive because 2 negatives would make a positive. So you're welcome to do that, but it is not necessary. All right, then the integral of e to the u du is itself. And now all I have to do is plug in the bounds, right? So remember, it's top minus bottom. E to the 0 is 1. It's better not to use a negative exponent. So that is one way to write the answer. Another way to write it is to get a common denominator. So that is also an appropriate answer. All right, and that concludes our lesson on using u-substitution for definite integrals.